As this week, a sunspot designated active region 4455, a region classified with an anti-Hale magnetic configuration, meaning its polarity runs in direct opposition to every other sunspot in its hemisphere, fired an X1 O-class solar flare, the most powerful category of eruption our star produces, and it did so after already detonating an M9, 3 at 1:36 UTC and an M7, 7 at 7 o'clock UTC earlier that same day. 3 major eruptions in 10 hours and 22 minutes from a single anomalous reversed polarity region on the surface of the Sun. NOAA's Space Weather Prediction Center confirmed all 3 events as Earth-directed. The faster CME from the X-class flare is now overtaking the slower cloud from the M7, 7 eruption. When they merge and the NOAA modeling confirms they will, the combined structure becomes what scientists call a cannibal coronal mass ejection, one eruption devouring another, amplifying its magnetic energy, and arriving at Earth's magnetic boundary as a single, supercharged plasma wall. That wall, according to NOAA's Space Weather Prediction Center, is arriving tonight. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: USGS, NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the GOES 19 satellite instrument record, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them before any decision is made, whether personal, professional, or otherwise. Verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us, but that is not even the complete picture. Because what the headline describes, a Cannibal CME Aurora over 23 states, a G3 or potentially G for geomagnetic storm watch, is only the visible surface of something far older, far more complex, and far more consequential than any single Aurora event. Beneath that headline lives the story of a sunspot that should not exist, behaving in ways the standard models did not fully predict, producing eruptions that physicists describe as harder to forecast precisely because their magnetic architecture violates the norms of the current solar cycle. Beneath that lies the story of an interconnected planetary system, magnetic field, ionosphere, power grid, satellite constellation, GPS infrastructure that modern civilization has built with an assumption of solar quiet that the sun has never actually agreed to. And beneath all of that is the story that the geological and historical record has been trying to tell for centuries, that what is happening tonight is not unusual in the life of this star. It is, in fact, routine. What is unusual is that 7 billion people have chosen to build a world that cannot easily survive it. Active region 4455 carries what solar physicists designate an anti-Hale configuration. To understand why that matters, you must first understand what Hale's polarity law says. In any given solar cycle, sunspots in the northern hemisphere follow a consistent magnetic polarity pattern, leading edge positive, trailing edge negative, or the reverse, depending on the cycle, and this pattern flips with each new 11-year cycle. It is one of the most reliable patterns in solar physics, established by astronomer George Ellery Hale in 1919. Anti-Hale sunspots violate that law. They run their magnetic poles backward, reversed against the cycle's established current, creating what researchers describe as unusually intense magnetic shear attention in the field lines that stores more energy before release and discharges it in ways that standard flare prediction algorithms are not fully calibrated to anticipate. Anti-Hale configurations appear in fewer than 10% of sunspot regions, according to the peer-reviewed literature. Region 4455 is one of them, and as the data from NOAA's Space Weather Prediction Center and the Watchers News Service confirmed on June 3, this region fired an X-class flare despite being initially assessed as relatively low complexity, a surprise that forecasters noted directly in their communications. In short, the sun did something the instruments did not fully expect, from a region built precisely to be harder to read, and then it did it 3 times in a single day. The Cannibal CME mechanism itself deserves to be held under the light. When the sun fires multiple CMEs in rapid succession from the same active region, the later, faster eruptions begin chasing the earlier, slower ones through interplanetary space. The medium through which they travel, the solar wind, is not empty. It is a constant outflow of charged particles streaming from the sun at approximately 400 to 800 kilometers per second on a typical day. A CME can travel anywhere from 250 to more than 3,000 kilometers per second. When a faster cloud overtakes a slower one, it does not simply pass through it, it compresses it, it merges with it. It absorbs the magnetic field structure of the earlier cloud and carries it forward as part of a now larger, now more energetic combined structure. The result is a single merged front that arrives at Earth's magnetic boundary, the magnetopause, with more total magnetic energy than either eruption carried alone. NOAA's modeling, confirmed by coronagraph imagery reviewed by EarthSky and the Watchers on June 4, shows this merger is in progress for the 2 Earth-directed components of June 3E's sequence. The combined arrival is expected to drive geomagnetic storm conditions to G3, with G for possible depending on the southward orientation of the merged cloud's magnetic field at the moment of contact. The KP index, the planetary geomagnetic index used by NOAA to classify storm severity, runs from 0 to 9. G1 storms correspond to KP values of 5, G3 corresponds to KP7, G4 corresponds to KP8, G5 the most extreme classification, reserved for events like the May 2024 storm and the notorious March 1989 event corresponds to KP9. The difference between G3 and G4 is not a matter of degree, it is a matter of category. At G3, high-frequency radio can be intermittent, GPS accuracy degrades, and satellite operators begin protective maneuvers. At G4, power grid operators in mid-latitude regions face potential voltage instability, satellites experience surface charging that can damage electronics, and Aurora can be seen as far south as Alabama, Georgia, and Texas under dark skies. The distinction tonight rests on a single variable, the orientation of the merged cloud's interplanetary magnetic field at the moment it reaches the L1 monitoring point, the pair of spacecraft positioned 1 million miles from Earth directly in the solar wind stream that serve as humanity's only early warning system for what is about to hit the magnetosphere. That data will not be fully interpretable until the CME is already en route to impact. NOAA's Space Weather Prediction Center stated clearly that the G3 watch was issued with the understanding that G4 conditions remain possible. The distinction between those two outcomes will not be known with certainty until real-time solar wind readings from those L1 instruments show whether the interplanetary magnetic field is oriented northward, largely deflecting Earth's magnetosphere, or southward, in which case it connects directly to Earth's field in a process called magnetic reconnection, opening a channel through which the full energy of the merged eruption can pour. And here is where this account becomes genuinely significant. The communities that will feel this event first are not concentrated in one place. NOAA's Aurora visibility forecasts for a G3 to G4 storm identify 23 states in which the northern lights may be visible, stretching from Washington state and Montana in the northwest through the Dakotas, Minnesota, Wisconsin, Michigan, through New York and Maine in the northeast. In places like Duluth, Minnesota, population approximately 90,000 people living on the western tip of Lake Superior, residents may look north tonight and see the sky moving in curtains of green and red. In Grand Forks, North Dakota, population 57,000, the aurora may be directly overhead. These are cities built on flat, open terrain with dark skies outside their centers, and people who have stood in the cold before to watch this phenomenon and called it extraordinary. They know what this looks like. But what they may not know, what most people watching an aurora display from a field outside their town do not fully consider in that moment, is that directly above their heads, the planet's magnetic shield is being compressed. The magnetopause, which normally sits roughly 10 Earth rad from the planet's center on the sunward side, can be pushed inward to as close as 5 to 6 Earth rad during a severe storm. During the G5 event of May 2024, the magnetopause was compressed to historically unusual levels. Tonight, depending on the storm's realized intensity, that compression will happen again over those same quiet towns, those same flat fields, those same people standing in the dark looking up at something beautiful while the infrastructure beneath their feet registers the cost. Because the system is not inactive, it is accumulating. Every high-frequency radio operator on the night side of Earth during a G3 or G4 event knows what accumulating means. It means degraded signal. It means intermittent blackout. For aviation, it means rerouting polar flight paths, a procedure carried out routinely by major airlines during severe solar storms, adding hours to transatlantic flights and thousands of dollars in operational cost per aircraft. For satellite operators, it means commanding attitude adjustments to prevent solar panels from saturating and monitoring surface charging levels that, if unchecked, can discharge in ways that damage onboard electronics permanently. For GPS-dependent precision agriculture systems, the autonomous tractors and field mapping systems that operate across the American Midwest, it means positional drift that cannot be corrected mid-operation. And for the power grid operators managing transmission infrastructure across the northern tier of the United States and Canada, it means watching for geomagnetically induced currents. The ground-level electrical currents that flow through the Earth's crust during severe magnetic disturbances find their way into the long-haul transmission lines running between cities and inject low-frequency DC current into transformers designed to handle only alternating current. When that happens at sufficient magnitude, transformers overheat. If they overheat long enough, they fail, and the transformers most at risk, the extra high voltage units sitting in substations serving millions of customers, cannot be replaced in days. The lead time for a new EHEV transformer is, in many cases, measured in months. 2 over a year. This is not a hypothesis, this is documented in the geological and engineering record. On March 13, 1989, a coronal mass ejection originating from NOAA active region 5395, associated with an X-15 class flare, one of the most powerful flares of the 20th century, struck Earth's magnetosphere at a speed of approximately 1,320 km per second. The KP index reached 9. The DST index, a measure of the intensity of the equatorial ring current generated by trapped charged particles, reached a minimum of negative 589 nanotesla. That number represents one of the most severe magnetic compressions recorded in the modern instrument era. At 2:44 local time in Quebec, Canada, the geomagnetically induced currents flowing through the Precambrian rock shield underlying the province found a more conductive path through the long 735 kilovolt transmission lines of hydro. In less than 90 seconds, the James Bay network went offline. 21 gigawatts of generating capacity vanished from the grid. 6 million people lost power. The blackout lasted 9 hours. The Montreal Metro was closed through the morning rush. Dorval Airport was shut. Schools did not open. breakfast was cold for a province that had gone to sleep with the reasonable assumption that the lights would be on in the morning, and that storm, the one that brought down Quebec in 90 seconds, was a G5 event. What is arriving tonight has been forecast by NOAA at G3 to G4. The margin between Quebec 1989 and the current event is real, but the infrastructure connecting them, the same long transmission lines, the same EHEV transformers, the same reliance on GPS, the same satellites operating in low Earth orbit with their solar panels exposed to the charged particle environment is, in its fundamental design, the same. The question is not whether the infrastructure is vulnerable. The question is what the southward component of the interplanetary magnetic field actually reads when the Cannibal CME arrives at the L1 Sentinel. Now pull the camera back further, because active region 4455 is not finished. NOAA's Space Weather Prediction Center noted on June 4th that solar activity is expected to remain at moderate levels through June 5th, with M-class flaring likely and a slight chance of additional X-class activity. The main source regions for additional strong flares are listed as regions 4455, 4458, 4461, and 4462, meaning the Sun is not running a single active region but an ensemble of unstable magnetic systems simultaneously. And EarthSky's June 4th solar news report noted that a component from the M3 flare on June 2nd may arrive on June 6th, potentially adding an additional round of enhanced geomagnetic activity atop the lingering effects of the Cannibal CME passage, that is 3 days of consecutive solar disturbance arriving in sequence. The magnetosphere does not fully recover between strikes. Each successive event finds a magnetic environment that is still settling from the last one. This is how historically severe compound events develop, not through a single catastrophic strike but through a sequence of moderate to strong impacts that keep the system from returning to baseline. There is another dimension to what region 4455 represents that the standard coverage tends to understate. The anti-Hale configuration, the reversed polarity that makes this region anomalous, is not merely a forecasting inconvenience. It reflects a fundamental property of how solar magnetic energy is stored and released. Standard flare prediction models are built on decades of data from Hale-compliant regions, their thresholds, their warning metrics, their confidence intervals, all calibrated to a baseline that anti-Hale regions do not conform to. A region like 4455, assessed at relatively low complexity but capable of firing X-class eruptions, represents a gap in the model. The literature on anti-Hale sunspots, some of which appeared in fewer than 3% of flare-productive regions, according to one classification referenced in specialist commentary on the June 3rd event, suggests that these regions produce flares that are not only stronger than their magnetic complexity metrics suggest, but that develop more gradually, releasing energy across a broader time frame. The extended flare profile noted by observers on June 3rd is consistent with this behavior. The energy burns itself in. It releases more slowly, across a longer duration, delivering sustained electromagnetic and particle flux rather than a sharp impulsive spike. There are approximately 2,000 active satellites in low Earth orbit. Their orbital mechanics are calculated with high precision. But during a severe geomagnetic storm, the upper atmosphere, the thermosphere, expands. The drag on satellites in low Earth orbits between 300 and 600 kilometers altitude increases as a result. Orbits that were predicted to be stable for days or weeks begin to decay faster than the models expected. Operators must expend propellant to correct. For satellites without propulsion, a category that includes a significant fraction of small commercial and research satellites, orbital decay simply accelerates. During the G5 storm of May 2024, SpaceX reported atmospheric drag disruptions to its Starlink constellation. The same physics apply tonight at G3 to G4 levels, scaled proportionally. The integrated global positioning system, the infrastructure on which shipping logistics, aviation approaches, financial transaction timestamps, and emergency dispatch services depend, will experience degraded accuracy in the highest storm phases. NOAA's G3 storm documentation states explicitly that intermittent satellite navigation GPS problems are expected. Its G4 documentation states that GPS systems could experience navigation solution issues. And now think about the person driving a delivery truck in Fargo, North Dakota tonight, population 125,000, situated on the Red River Valley alluvial plain, sitting directly under the projected Aurora band for a G3 to G4 event. Their GPS unit may give them a position that is off by meters. In normal life, that is trivial. In a construction zone or navigating an unfamiliar road in darkness, it is less so. The person managing an automated irrigation system on a farm outside Bismarck may see their GPS-guided pivots drift from their tracks. The emergency dispatcher in Duluth coordinating a medical response may find their GPS-based unit tracking system lagging behind reality by seconds that matter. These are not catastrophic failures. They are the 10,000 small degradations that never make a news headline but that collectively represent the cost of a civilization that has rewired its logistics around the assumption of constant satellite signal availability and then encountered a star that operates on a schedule of its own. The Carrington event of September 1, 1859 is the reference point against which all modern solar storms are measured. The astronomer Richard Carrington observed a brilliant white flare from his observatory in Redhill, England at 11:18 UTC, approximately 17 hours and 40 minutes later, an extraordinarily short transit time that implies a CME velocity of approximately 2,300 kilometers per second. The wavefront struck Earth's magnetosphere. The DST index reconstructed from historical magnetometer records reached an estimated -852 -1,760 nanotesla, numbers so extreme they exist at the edge of what any instrument of that era could measure. Telegraph operators across North America and Europe reported that their lines had become electrified by the storm's induced currents, that they could disconnect their batteries and still transmit messages, powered entirely by the geomagnetically induced current flowing through the wire. In some offices, the current was so strong, it sparked and set the equipment alight. That event was approximately twice the intensity of the 1989 Quebec storm, and the 1989 Quebec storm was a G5 event that took down a provincial power grid in 90 seconds and left 6 million people without electricity for 9 hours. The Carrington event, occurring today, would not damage a telegraph system. It would strike a civilization that runs its water treatment, its hospital equipment, its air traffic control, its financial clearing, and its military communications through a single interconnected electrical and communications network with long-haul transmission lines perfectly sized to serve as antennas for geomagnetically induced currents at continental scale. Scientists choose their language carefully here, and that careful language is itself the warning. NOAA's G for documentation does not say the power grid will fail. It says voltage irregularities are possible. It says false alarms may be triggered on protection devices. It says surface charging on satellites can occur. The language is measured. It is probabilistic. It acknowledges that most of the time, even in G for conditions, the grid holds, the satellites survive, the GPS degrades and then recovers. But the word possible is doing enormous work in that sentence, because what makes this moment consequential is not the probability that any single outcome occurs tonight. It is the cumulative probability across the remainder of solar cycle 25, which NOAA, NASA, and international solar physics agencies have confirmed reached its peak activity phase, that a combination of active regions, each carrying the potential of R445, will produce an event that exceeds what the infrastructure was designed to absorb. What the official data actually shows is that we are not at the tail end of this solar maximum. We are in it. The Sun's 11-year cycle, which began ascending from its minimum in December 2019, reached predicted peak intensity levels in 2024 and 2025, with activity continuing into 2026. Region 4455 is not an artifact of a passing phase. It is a product of a sun that remains energetically elevated, that is rotating new active regions into Earth-facing positions every 2 weeks as it turns on its axis, and that carries on its surface additional regions 4458, 4461, 4462 that NOAA identifies as capable of contributing further strong flares. Before this week ends, the system is accumulating, the baseline is not quiet. And the Cannibal CME arriving tonight is not the last word the sun intends to speak in this cycle. There is a final element to this picture that connects the solar storm to the broader geophysical environment in ways that are still under active research, but that verified data supports in principle. The magnetosphere's response to solar disturbances is not uniform across Earth's surface. It depends on the conductivity of the underlying geology. The reason Quebec's Precambrian shield made it uniquely vulnerable in 1989, while other regions with more conductive soils experienced the same storm with less dramatic grid impact. The northern tier of the United States, Minnesota, Wisconsin, Michigan, the Dakotas, sits on geological formations that share characteristics with the Canadian shield. This is not coincidental. The Laurentian basement rock that underlies much of the upper Midwest is the same ancient Precambrian craton that made Quebec's transmission system so vulnerable. The geomagnetically induced currents that flow through low-conductivity rock find their preferred path through the high-voltage transmission lines sitting on top of it. The physics that brought down hydro in 1989 does not respect a political border. The same geological substrate that runs north of Lake Superior continues south into Minnesota. The transmission infrastructure built across that substrate, the long-haul lines running between Minneapolis and Duluth, between Bismarck and Fargo, between Green Bay and Chicago, carries the same exposure to GIC intrusion that Quebec's transformers experienced the night the James Bay network went offline in 90 seconds. This has already happened once, and the record of it is still preserved in the engineering postmortems and in the physical damage to the transformer windings recovered from hydro E's substations in March 1989. It is preserved in the insurance claims from New Jersey, where a transformer at the Salem Nuclear Generating Station was damaged by the same storm S-induced currents. It is preserved in the EPRI conference proceedings from 1989, in which utility engineers from across North America compared notes on an event that none of their system designs had anticipated at that magnitude. The monitoring is in place and detection is possible, but prediction is not. That sentence must be understood precisely. NOAA can detect the CME at L1 approximately 15 to 60 minutes before it reaches Earth's magnetosphere, 15 to 60 minutes in which grid operators can be notified, protective relays can be adjusted, and satellite operators can place spacecraft in safe mode. That is not nothing. It is in fact the product of decades of investment in space weather monitoring infrastructure. But it is not prediction in the sense of knowing 24 hours in advance whether tonight's storm reaches G3 or G4, whether the interplanetary magnetic field arrives oriented northward or southward, whether the transformers in northern Minnesota experience a transient that trips a relay or one that saturates a winding. Those outcomes depend on the precise magnetic field geometry of the merged Cannibal CME, which cannot be measured until the event is already underway. Minutes are not hours, and in this context, that difference is everything. 15 minutes is enough time to notify. It is not always enough time to reconfigure a grid that serves millions of customers across 3 time zones. And so tonight, as the Aurora moves across the sky above Grand Forks and Duluth and the farmland outside Bismarck, the question those communities would ask if they had access to the data in front of you right now is not whether the lights in the sky are beautiful. They are. They always are. The question is the one that no instrument yet built can fully answer in advance. What is the orientation of that magnetic field right now as it crosses the orbit of the Moon and approaches the narrow detection window at L1, and what will it do to the transformers, the satellites, and the grid when it arrives? The Sun fired 3 major eruptions from a single anomalous sunspot in less than 11 hours. One of those eruptions devoured another in interplanetary space and is arriving as a combined amplified wave. NOAA has placed a G3 storm watch in effect with G for conditions possible. 23 states may see the Aurora tonight. And somewhere in the processing center of a mid-latitude power utility, an engineer is watching the real-time magnetometer data, waiting for the first sign of the CME's magnetic field orientation, knowing that what arrives in the next few hours will determine whether tonight is a light show or something the engineering record will document for the next generation of grid designers to study. The last solar cycle minimum occurred in December 2019. The current cycle's peak is underway. Region 4455 is still in partial Earth-facing rotation. The Sun, which has been doing this for approximately 4.6 billion years, will continue to do it regardless of what any instrument built in the last century measures, and will keep doing it long after the last transformer mankind has ever built has turned back into rust and the last power grid has returned to the soil from which its copper was mined, not because the Sun is hostile, but because it is indifferent, operating on timescales that make a G for geomagnetic storm nothing more than a Tuesday in the long and patient life of a middle-aged star.